In our lesson today, we will discuss about diffraction gratings. A diffraction grating consists of thousands of parallel slits etched on glass so that brighter and sharper patterns can be observed than with Young's experiment. The equation is similar to the Young's experiment. So this is a diffraction grating. We can see some diffraction gratings here with 80 lines per millimeter, 100 lines per millimeter, and so on. The equation itself is d times the sine of theta equals n lambda. We have derived this equation before, and n starts from 1. So this is the grating equation. I would like to explain that d here. Before in the Young's experiment, d is the distance between two slits. Here, d is the slit width or the slit spacing. Lambda is still the wavelength of light. Theta is the angular deviation. N is the order of fringe. And d is equal to 1 over n, where n is the number of lines per unit length of grating. So here I have a compact disc, a CD. It acts as a diffraction grating. The colors and the intensity of the reflected light depend on the orientation of the disc relative to the eye. I will give you some examples from your book. This is the example problem in your book on page 195. A diffraction grating with 3000 lines per centimeter is used to determine the wavelength of a monochromatic light. So this is the capital N, 3000 lines per centimeter. The angle between the central bright and the first order bright is 8 degrees. The sine of 8 degrees is given 0.14. So from this N, we can find the D, the width of the slit width, the slit spacing. 1 over N, because this is per centimeter, we have 3000 lines. Then in 1 meter, there will be 300,000 lines. So D is 1 over 300,000 in the unit of meter. And this 8 degrees is the theta, 8 degrees. We want to find the lambda. This is the first order, so small n is equal to 1. And we have this equation, d times the sine of theta equals n lambda. That d is 1 over 300,000 times the sine of 8 degrees equals 1 times lambda. Then you can calculate lambda to be 4.67 times 10 to the minus 7 meters. The next example is taken from the more problems question on page 199. I would like to discuss number 8 and number 9. Number 8, blue light is incident on diffraction grating with 6,000 lines per centimeter. So this is the capital N, 6,000 lines per centimeter. So the D is 1 over 600,000 in the unit of meter. The second order bright fringe, second order means that the N is 2, is formed at the deviation angle of 30 degrees. That will be the theta. We want to find the wavelength, the same as before. We use d times the sine of theta equals n lambda, and d is 1 over 600,000 times the sine of 30 degrees equals 2 lambda. The sine of 30 degrees is a half, so we can calculate lambda to be 4.17 times 10 to the minus 7 in the unit of meter. Number 9, white light is incident on a diffraction grating with 3,000 lines per centimeter. That will be N, the capital N. So D is equal to 1 over 300,000 in the unit of meter. A screen is placed at 50 centimeters from the grating, so that will be L, the distance from the grating to the screen. Calculate the width of the first order spectrum captured on the screen. So M equals 1. Given the wavelength of red light, 8,000 angstrom, or 8 times 10 to the minus 7 meters, because 1 angstrom is equal to 10 to the power of minus 10 meter. And that of violet lambda of violet equals 4 times 10 to the minus 7 meter, 4,000 angstrom. I can describe it as like this. We have white light, it incident on a diffraction grating, and that white light will be this is a polychromatic light. It will be dispersed into monochromatic light from red to violet. From this equation, d times the sine of theta equals n lambda. We can see that when lambda is greater, then here, when lambda is greater, then the sine of theta will be greater. That's why theta will be greater. Lambda of red light is greater than that of violet. That's why we can see here that the red light has, because it has a longer wavelength, then it will be further from the central bright fringe. So the nearest spectrum to the central bright fringe will be the violet, yeah, because it has a smaller lambda. Yeah, so in this case, this is the distance from the red spectrum to the central bright fringe. We call this y red. And the distance from the violet spectrum to the central bright fringe, we call this y of the violet. We have this equation, d times y over L equals n lambda. Remember that y over L is equal to the tangent of theta, where it is equal to the sine of theta when theta is very small from the previous video. So y is equal to n lambda L over d. So for the red light, y red is 1 multiplied by 8 times 10 to the minus 7, this one, multiplied by L, 0.5 meters, divided by D, 1 over 300,000 meters. And you'll get y of the red light is 12 centimeters, 0.12 meters. For the violet, the y of the violet is 1 multiplied by the lambda of the violet multiplied by L over D. So you will get 0.06 meters or equal to 6 centimeters. So the width of the spectrum will be from this to that. And that will be equal to y red minus y violet. So it will be 6 centimeters, this one. From this to this. This is the width of the spectrum. Okay, now you can try to do yourself the multiple choice questions on your physics textbook on page 201. Please do number 1 until number 6 as your exercise. If you have any question, you can always contact me. Thank you for your attention. I hope this video is useful.